Actually, I'm sorry. I meant to change the title is supposed to be Beyond Quadratic Chabauty. But I forgot to change the title in here. Anyway, Beyond Quadratic Chabauty. So here's the overview of the talk. So I adapted it to an audience that I understand has been learning all about non-abelian Chabauty last week. And so first I'm going to sort of motivate the general problem. Then I'll talk about some concrete results, including some that follow from what I'm actually going to talk about. And then parts 3 and 4, I'll get into the actual technical details of what we're doing to go beyond quadratic Chabauty. Okay. So, point of doing higher or beyond quadratic Chabauty is really because of Falting's theorem. Now, I just like to set notation and note that Falting's theorem is about rational points on proper higher genus curves. Siegel's theorem is about S-integral points on affine curves, but they actually have a common generalization, okay? And so the common generalization says that S-integral points are on a hyperbolic curve are finite. Now, if X is proper, then integral points and S-integral points and rational points are the same. So that's where you get Falting's theorem. Now, what do I mean by hyperbolic curve? So there's a nice unified definition. For a proper curve, it means the genus is at least 2. But in general, it simply means that the manifold has negative Euler characteristic, I mean the complex manifold, or equivalently, that it has non-abelian fundamental group. And so a big open problem is to be able to compute this finite set given X and R. And then I should say, really, it's the case of higher genus curves that's much less known. So, non-abelian Chabauty, to review a little bit, and what's important for us, is that it defines a series of sets of p-adic analytic functions on the p-adic points of the curve that vanish on the S-integral or rational points. And so therefore they're zero sets. These are the zero sets of those sets of functions, okay, are nested like so, and contain X of R, which we're trying to find. Now, there's a general fact that also sort of follows from Kim's theory, that if the ranks of certain generalized Selmer groups, depending on n, are not too large, okay, then there are non-zero functions, which means that the zero set of these functions is actually finite. This has to do with the fact that X is a curve and X of QP is one-dimensional. So, and it's one-dimensional, it's also going to be proper. I should have said ZP rather than QP. So sorry for that oversight. But one way we want this to be compact so that the zero sets of functions are finite. Now, conjectures on Galois cohomology imply that these bounds on generalized Selmer groups hold, in the sense that for n sufficiently large, we have a non-zero function, meaning that you get, once you have a non-zero function, you can use Newton's method to calculate its zero set, and you get an explicit bound on the number of rational points. And more specifically, you get some information on where they lie p-adically. Now, the quadratic Chabauty method, which you've also been hearing about, is really in the case that n equals 2. Okay, and there's a lot that can be done in the case n equals 2 because of the relation to p-adic heights. And so my overarching goal, and the point of this talk, is about computing these sets of functions for n greater than 2. Let's say for a general n. So let's first of all say why doing this leads to effective faultings. So there's this conjecture of Kim that for sufficiently large n, in fact, the only common zeros of these p-adic analytic functions are precisely the integral or rational points, okay? Meaning that you have enough functions to cut down not a finite set containing the rational points, but rather all of them. And so if we want to talk, let's say, just specifically about effective faultings over Q, so this is in the case of a projective curve, proper curve, then what we would do for effective faultings is we're given a proper curve, we embed it into projective space, and well, one thing you can do is you can just simply search explicitly for points. So just write down, list all of the points in the rational points in Pn, and then just keep checking them one after the other to see which ones are contained in X. And so that gives us pretty quickly a finite set. And the idea, well, like once you do it to, pretty high heights, usually you basically find, maybe you find 3 rational points on X, and you're pretty sure that's all of them. But what you need to do to prove that that's all of them is to bound the set of rational points on X, which is exactly what these p-adic analytic functions are for. And so the idea is then by day, we sort of do these processes simultaneously. We compute ICKN for larger and larger n, and then we can use some methods in p-adic analysis to bound the set of common zeros of these functions. And then the idea is that if our list that we compose at night has the same size as the bound that we get by day, we're done. We have provably determined the set of rational points on the curve. Okay, so that's why we are really interested in computing ICKN or ICKNR. So let's talk about some results in computing ICKNR that go beyond n equals 2. Okay, so some results that sort of so far exist in terms of going beyond quadratic Chabauty. So and I meant to mention this, but yeah, I mean, one reason, that people here might be interested in provably finding the set of rational points on some algebraic curve is because we're interested in modular curves. And finding the set of rational points on some modular curve tells you the set of possible elliptic curves with some sort of specific torsion data. Great. So, turns out that although higher genus curves are our interest, the simplest case of a hyperbolic curve, specifically an affine hyperbolic curve, is P1 minus 3 points. Okay, it turns out that as long as you take 3 points out of P1, the fundamental group becomes non-abelian, or the Euler characteristic becomes negative. You have to take a full 3 points out. Okay, and it turns out that integral points, let's say if we're in a ring R on this X, is the same as finding pairs of units in R whose sum is 1. Okay, this is known as the unit equation. And this was proven finite a long time ago, but then when Min-Young-Kim reproved it in 2004, that was the first test case for his non-abelian Chabauty method. And I should note that I'll refer to this later, that the associated Galois representations or motives are what's known as mixtate, meaning they come from iterated extensions of powers of the cyclotomic character, at least in Galois theory. So this is called the mixtate case. Okay, and so then a lot of the more recent work is trying to generalize from the mixtate case. But let me first tell you what has been done in the mixtate case. Okay, so as you know, in the non-abelian Chabauty method, you involve p-adic iterated integrals. For x equals p1 minus 3 points, you get p-adic polylogarithms. They're p-adic versions of classical polylogarithms. More specifically, they satisfy the same differential equations as classical polylogarithms. So the work of Danko and Wevers, before I got involved, first of all, here's a function for n equals 2. So this is maybe a sort of a proto-quadratic Chabauty that you can use to deduce this. But for n equals 4, they also found something. Okay, and it looks pretty complicated, but this is great. This is beyond quadratic Chabauty. And in some sense, the method they use, or the refinement of the method that they used by myself and Don Cohen, is the inspiration for all of the further work. Great. So let me just review a few more results. So Don Cohen also developed sort of the idea of turning their method into an algorithm, not just computing specific examples, but actually making an algorithm. When I got involved with Don Cohen, we computed a new function, which was instead of, so over here we had R is Z adjoin 1/2. In our work is R is Z adjoin 1/3. There's some reasons why this is actually conceptually more difficult, having to do with the fact that, in particular, that there are no Z adjoin 1/3 points. So in particular, we had to deal with what happens when you don't have enough integral or rational points, which is important in the general context. And I should just note that there's a relation between this stuff and special values of polylogarithms, which is a whole topic that on which there's a lot of work, for example, by Don Zagier and later Herbert Gongel. Okay, so then one of the things that we did in our work was we were verifying cases of Kim's conjecture, the one that I mentioned earlier. We have an article making an improved algorithm. Now, let me say something about the way the algorithm works, because this is going to be, when we eventually hope for an algorithm for higher genus curves, it's going to be of the following form. So the halting of the algorithm depends on Kim's conjecture and maybe also some other conjectures. Okay, you need those we can't prove the algorithm halts. However, if the algorithm halts, if we do the algorithm and it halts, then we've provably gotten the correct answer. I should say that there's a little caveat in that when you go to higher genus curves, there's going to be some extra conjectures that we sort of can't get around in this way, specifically the Bloch-Kato conjectures, which you can prove in some context using Iwasawa theory. But at least there's sort of, with Kim's conjecture, the idea is Kim's conjecture suggests that the method will always work, but you don't need it to make the method work. Okay, so let me say some explicit things, some explicit concrete results of the theory that I'm going to go into in parts 3 and 4, but just to sort of give you a taste of what this can lead to. So another case of a hyperbolic curve is an elliptic curve with a point taken out. Okay, elliptic curve has Euler characteristic 0. You take out a point, you get Euler characteristic -1. Okay, and rational points, or integral points, or S integral points, basically means finding S integral solutions to the Weierstrass equation. So this is also something that was proven by Siegel, reproven by Kim, not in general, but only when E is Cm. That's because the Iwasawa theory becomes more simple when E is Cm. And I should say this is the simplest non-rational case of Chabauty-Kim. I should also say it's the simplest non-mixed Tate case of Chabauty-Kim. So it's really a good stepping stone to higher genus curves. Okay, let me just make sure people hear me and all. People hear me?
Can hear you.
Yeah, actually, and how much more time do I have, by the way?
You have just finished only 15 minutes, so you have 45 minutes more.
Okay, I have 45 minutes more. Great. Okay, so anyway, so
yeah, I just wanted one question. When you're talking about this algorithm halting, is there some specific conjectures like the finiteness of Tate-Shafarevich kind of conjectures here to say when the algorithm halts?
Okay, so I see what you're saying. So the conjectures that imply that the algorithm halts are basically going to be Kim's conjecture, and maybe certain conjectures about certain Hopf algebras of Motivic periods being generated by certain specific kinds of Motivic periods, which maybe you can sort of say is a conjectures of the form that all Galois representations satisfying some abstract condition come from some specific geometric situations. However, there's a further conjecture called Bloch-Kato conjectures, which in the higher genus case we're just going to need to assume, and those conjectures are, you could say, a generalization of the conjecture that the rank of the Mordell-Weil group is the same as the P-Selmer rank, like p-adic P-Selmer rank. And so the finiteness of Tate-Shafarevich implies that the Mordell-Weil rank is the same as the rank of the p-adic-Selmer group. And so the point is, what we need is really the Bloch-Kato conjectures, which are generalizations of that, which say something similar for higher Chow groups and generalized Bloch-Kato-Selmer groups for Galois representations. I'll say a little bit later about what conjectures exactly you need, or what form of Bloch-Kato conjectures you need. In fact, you only need the cases where the corresponding Chow groups are zero for trivial reasons. But the conjecture is non-trivial. Anyway, I'll mention that a little bit later. Okay, but the Bloch-Kato stuff is sort of a generalization of the Shah being finite. You could think of it that way. Great. So, anyway, concrete result, okay, for elliptic curve. So this is, I mean, I sort of did most of the details relating to it in 2021, but it relies there's a very technical dependence on a result of myself and Dan Cohen that's coming out around now. A result that I'm going to describe later about a p-adic period map. But anyway, the concrete thing that you get from this is, so let J1 through J4 be basically some p-adic functions on E defined by iterated integrals. So you see you have two concrete differential forms, and you have all these iterated integrals in these differential forms. Okay? And so the theorem says basically that if E is an elliptic curve of P-Selmer rank 1, I should note that then I'm not actually using finiteness of Shah, because I'm just, making the condition about the P-Selmer rank. If I wanted to say Mordell-Weil rank 1, then I need finiteness of Shah to say that the P-Selmer rank is also 1. But in practice, we know how to compute P-Selmer rank, so we can just verify that it's 1. And this is sort of what you need from Bloch-Kato. You need that the value at 2 of the p-adic L function is non-vanishing. Okay, so what you do is you use that and some Iwasawa theory to show that whatever case of Bloch-Kato you need. Then there is a function of a fairly simple form. There's only sort of 5 unknowns, okay, which vanishes on the z-adjoin 1 over L points. Okay, and so this is kind of the thing that well, in progress is what we eventually, maybe the next step next year or something is hopefully really compute this explicitly for some specific elliptic curves. And then when I write projective examples, what I mean is essentially extend this to higher genus curves. Now, the method gives you a little bit more information about the CI. It's not just some p-adic numbers, and I will actually say more about it a little later. But for now, I'll just give you what I call a bonus slide, that there is a more explicit expression or for that function from before. So remember, before you have J4, J3, J1, J2, J1 to the third, and J1 with some undetermined p-adic coefficients. Here, turns out that I have a certain way of expressing them, which you're not going to understand what these Fs mean. I'll say a little bit about that much later. But let me say it just a little bit, is that some of them, like F pi I, is going to be basically integrals from this B should be O, from the base point of the elliptic curve to a generator of the Mordell-Weil group of these differential forms. They're sort of p-adic logarithms, or elliptic logarithms of the generator of the Mordell-Weil group. You also have just a p-adic logarithm of L. And then you have something that's related to a symptomic regulator from some larger K-theory group, K2 of E. Okay, and that relates the whole picture with the Bloch-Kato conjectures. Okay, so there is more information on these coefficients, but my theorem is just sort of about there being these coefficients. Great. I won't get into this slide, but point is there's some Iwasawa theory relating this condition about the p-adic L function to the vanishing of some Bloch-Kato-Selmer group. So if you just look at the very first line of this slide, this condition of non-vanishing of the p-adic L function is used to show vanishing of a certain Bloch-Kato-Selmer group. Great, which is basically some sort of Galois cohomology with local conditions. Great. So now I'm going to get into the meat of what allows me to deduce results like this. And this is what I call the theory of Tanakian-Selmer varieties. So let's first motivate. Okay, so why do we need Tanakian-Selmer varieties? Or in other words, why is it hard to compute ICKN? Okay, well, let's go back to Kim's diagram, or Kim's cutter, as I understand you've seen. So we have the let's just say, let's not worry about, affine curves. Let's just say it's a proper curve for simplicity. And let's look at x of q inside. Oh, and also, yeah, let's assume that k equals q. And let's say we have x of q inside x of qp. We have kappa, the non-abelian Kumar map, or non-abelian unipotent Albanese map, as it's called, to the Selmer variety, H1FS. I'm not worrying about the Betz-Dogra stuff right now. So we're assuming that X has good reduction outside S. And we have this localization map, which is really localization composed with the Bloch-Kato logarithm, to the de Rham unipotent fundamental group modulo F0. Okay. And so where does ICKN fit into this? Well, it's the pullback under kappa P of the ideal of functions vanishing on loc n. And so really, in some sense, the goal is to compute loc n, or more specifically, to compute loc n in coordinates where we know kappa P. Okay, and then kappa P is not too hard to compute in at least some coordinates. It's just in terms of p-adic iterated integrals. Now, the two problems with computing loc n, or especially with understanding the lower left object in this square diagram, is first of all that the Galois group of q bar over q is really big and complicated. Some people would say that the whole theory of number theory, or at least algebraic number theory, is understanding this group. And so when I say, the Bloch, I think if you learn about, you did non-abelian Chabauty, so hopefully you mentioned, Bloch-Kato-Selmer conditions. That's for defining the Selmer variety here. And so these Selmer conditions, well, away from P, it's just going to be something like unramified outside S. But at P, okay, you have this p-adic Hodge theory condition, this crystalline condition. So it's defined by this p-adic period ring B Chris, which is really big and complicated. Okay, so these two things are really big and complicated and make it difficult to explicitly understand the Selmer variety. And so it turns out that using a bit of Tanakian formalism, we can actually, in fact, kill two birds with one stone, as we say in English. We can actually sort of solve both of these problems at the same time. And so the idea is to consider the category of all relevant representations of the absolute Galois group. And first of all, when I say relevant, I mean only representations that are crystalline. So this crystalline condition is going to be built into the category. And once we understand the category, we don't have to worry too much about this B-Chris, this crystalline p-adic period ring. And also when I say relevant, I mean not all representations satisfying the correct local conditions, but representations that basically are closely related to the given curve. In particular, that have that are iterated extensions of tensor powers of the Tate module of the Jacobian of X, where X is our curve. So, precise definition, okay, as I define this category rep SFS, QP, GQJ. So it depends on this J. And it's a category of geometric Galois representations, where geometric is in the sense of Fontaine-Mazer. That's just basically, unramified almost everywhere, de Rham, stuff like that, with a weight filtration. So I'm requiring all of my representations to have, to have a weight filtration where the weight graded pieces have the appropriate weights in the sense of the Weil conjectures, or Deligne's work on the Weil conjectures, but then more specifically, such that the graded pieces are in the Tanakian category generated by the QP Tate module of J. Okay, so that's the key thing. And then I have a further condition, which is that the extension structure should be unramified outside S. In fact, since I assume that X has good reduction outside S, it turns out that VP of J is unramified outside S, so all the representations are unramified outside S, but there's a funny thing where you can have a situation where the representation VP of J is ramified at a place, but in some sense the extension structure is unramified. But that's a very, very non-important technical detail for you right now. So it turns out that this category is not actually all that difficult to describe. So its semi-simple objects, okay, first of all, are basically going to be the Tanakian category generated by the Tate module of J. And so its Tanakian Galois group is just what's known as the p-adic monodromy group of J, which I call math bold G. And the p-adic monodromy group, I mean, it's literally the Zariski closure in GL of the Tate module of the image of Galois. And at least conjecturally, it's closely related to the Mumford-Tate group. So if you know the Mumford-Tate group of an abelian variety, this is what it's closely related to that. And specifically for in the mixed Tate case, this group G is just GM. For a non-CM elliptic curve, this group G is GL2, just to give you a rough idea. Okay, so that's the semi-simple objects. And if you want to understand an abelian category, well, one way to understand it is to understand, first of all, the semi-simple objects, and then understand the extension structure, or in other words, how the semi-simple objects fit together. And I should say, like, this is specific. It's not just an abelian category. It's a like, a Noetherian and Artinian abelian category, meaning every object of this category has a finite filtration where the pieces are indeed simple. Okay, so really everything is built out of the semi-simple objects. Okay, and so then what are the extensions? So the X1s, and you can sort of get the X1s between any two objects using X1 from QP, meaning the unit object, to V. This is just a Bloch-Kato-Selmer group of V. Well, in fact, because of the way I define the category, for V of negative weight, it's the Bloch-Kato-Selmer group. For V of non-negative weight, this X group vanishes. I sort of define the category that way. Conjecturally, the Bloch-Kato-Selmer group also vanishes for V of non-negative weight, but that is a big conjecture. Okay? And then xi for I greater than or equal to 2, at least conjecturally, vanishes. I should say that actually this is not a problem. So all the calculations you do get around that conjecture. There's sort of a lot, like it's an annoying thing that I have to do, but basically, even if the conjecture is false, all my results are still true, because if the conjecture is false, it's actually better in some sense. Okay, so that conjectural part is not important, or the conjectural nature of that is not important. Okay, so what do we do with this category? We have this category of Galois representations. It's a Tanakian category. So what do we do with it? Well, we want a fiber functor. There's an obvious fiber functor, which is just take the underlying vector space. It turns out that for some purposes later, I actually want to take what I call the de Rham fiber functor, taking V to D Chris of V. I've assumed, I should say that like P is not an S, so what I'm really assuming that all the representations are crystalline at P. Okay, so we can really just take D Chris. And then by the Tanakian formalism, the category I defined is naturally the category of algebraic representations of a certain pro-algebraic group known as the Tanakian fundamental group. And in fact, the more explicit structure I mentioned, understanding the semi-simple objects, tells you that this group is an extension of G by a pro-unipotent group, which I call URJ. And furthermore, by the description of the category, URJ is a free pro-unipotent group on essentially the X1s, or more specifically, the X1s for irreducible V, simple, or aka simple objects of the abelian category. Okay, it's a free unipotent group on these Bloch-Kato-Selmer groups. Okay, so there's a fair, if you can describe Bloch-Kato-Selmer groups, and I'll say something about that in the next slide, you can pretty explicitly describe the group Pi1MA RJ. You can pretty explicitly describe this Tanakian fundamental group. So in fact, the idea is that all the complication with the absolute Galois group of Q and with the local p-adic Hodge theory conditions are bunched into the problem of computing these Bloch-Kato-Selmer groups. Okay, and there's actually a lot that can be said about those. But the upshot for the theory of Selmer varieties for non-abelian Chabauty's method is that now this Selmer variety, H1FS GQ with coefficients in UN, the one defined by Min-Young-Kim, is just the really algebraic group cohomology of the Tanakian Galois group with coefficients in the de Rham fundamental group, or the nth quotient of the de Rham fundamental group. So the right-hand side is what we call a Tanakian-Selmer variety. And in my write-ups, I do actually deal with all the Betz-Dogra stuff, but I don't want to do that here. So how do we compute the Tanakian-Selmer variety? Okay. So in fact, okay, let's put it this way. How do we compute this algebraic group cohomology here? Well, it turns out that there's this nice fact that is the same as G equivariant cocycles of the unipotent radical. Note that this is using the fact that G is reductive. So G is reductive, in some sense it has trivial cohomology. And so because of this, using that, we get this result. This was already a lemma in Danko and Wever's for G equals GM, and then I sort of extended it to a general reductive G. Okay. Now, the latter is, as I said, the space of G equivariant cocycles. But it turns out, in fact, that you can compute it more explicitly just by understanding the abstract structure of URJ and its G action. So more specifically, you can put at least some abstract coordinates on this space of cocycles. And so more specifically, for each V that's irreducible, or irreducible representation of G, we get a number of coordinates equal to the dimension of the Bloch-Kato-Selmer group. So you can actually, in fact, write it in terms of either a basis or a co-basis of the Bloch-Kato-Selmer group. And you get this for each copy of V contained in the unipotent fundamental group. Each copy of V contained in UN. Okay? So in terms of the Bloch-Kato-Selmer groups, we get actually a fairly explicit description of the Tanakian-Selmer variety. Now, I won't get into the details, but let me just say that the Bloch-Kato conjectures give you a way of conjecturally computing ds of V, computing the dimensions of these Bloch-Kato-Selmer groups. In the specific case that V is the Tate module of J, it's just conjecturally the Mordell-Weil rank of J. It turns out that for n equals 2 or weight minus 2, you compute them in terms of something like the genus and the Picard rank of J, something about the the fixed part of, or really the Galois fixed part of the Néron-Savary group of J. For n, for V that are of weight -3 or smaller, in fact, these dimensions just come out using some sort of Archimedean data. And so really just you sort of get stuff in terms of the genus. Okay. And so
I have a question. For the unipotent group, the cohomology should be essentially trivial, right? So you should reduce to cohomology of GM.
No, so this is cocycles from U. This is not cohomology from U.
Ah, okay.
It's cocycles. So somehow when you do this, you don't have to mod out by coboundaries when you're taking the G invariants. It's a funny thing, but it's a fairly abstract lemma. Okay. So the point is that you use the Bloch-Kato conjectures. And I want to mention that you can use Iwasawa theory to at least compute specific to actually in practice verify cases of Bloch-Kato. If we knew Iwasawa main conjectures in great generality, which relates to if we had Euler systems in great generality, we could, verify these in many more cases. I think there's some vague general formalism in which the existence of a certain kind of Euler system implies a way to computationally verify Bloch-Kato. And so if one is interested in doing the Iwasawa theory verification, it's useful to know which V we actually need, whether there's an Euler system for that V. And specifically for a given n, we need V appearing in all tensor powers of the Tate module of J up to the nth one. So mth tensor power for m from 1 to n. Okay, great. So that's up to here. That's about the Tanaki and Selmer variety. Now, let's talk about and really get into some of what's more joint work with Ishai Dan Cohen, localization and p-adic periods. Because after all, what did I say? I said that we have a way of computing at least abstract coordinates on this Tanaki and Selmer variety, which is basically the same as the usual Selmer variety. So in some ways, if we go back to the Kim's cutter, the Chabauty-Kim diagram, this sort of essentially gives us a way of putting coordinates on the lower left object. But we want to understand not just the lower left object, but the map loc n. Okay, that's also important. So, okay, well, so you might think that for the map loc n, that you have to do something p-adic. Okay, you're really taking some global Galois cohomology, and then you're taking some p-adic specialization as well as doing some p-adic Hodge theory. That's what we would have thought until some work of mine with Don Cohen in the mixed Tate case, some of our papers that came out around 2017, 2018, or 2018, 2019, something like that, which actually says that really everything that's interesting in the localization map, specifically the non-dominance of the localization map, appears already in what I call the universal cocycle evaluation map. What is this? Well, an element of the space of cocycles is a kind of map from URJ to UNDR, right? That's what a cocycle is, a kind of map. And so you can evaluate on a particular element of URJ, but in fact, you can talk about the universal evaluation map. So the evaluation map is from this space of cocycles cross URJ to UNDR. In other words, if I have a cocycle and I have a point in there shouldn't have been an X there. If I have a point in URJ, forget about that X there. Okay, we get an element C of U inside UNDR. Now, part of being universal is I want this to be relative to URJ. That turns out to be important. So in the second factor, I just project onto URJ. Okay, so I want this is not exactly the evaluation map. This is the evaluation map viewed as a map of schemes over URJ. So it lies over the identity map on URJ. Okay, and now what we can do is if we have a map from spec QP to URJ, in other words, if we have a special point, okay, of period P of URJ, we can pull back the universal co-cycle evaluation map along our map from spec QP to URJ, and that gives us a map from the Selmer variety to UN. And it turns out that that the sort of idea that we realized is that we sort of did it in the mixed Tate case, but we expected this to hold in general, and now we're close to where we've basically proven it, is that in fact the localization map can be defined by taking this universal co-cycle evaluation map, pulling back along a map from spec QP to URJ, and then, just as I mentioned in the footnote, composing with the projection from UN to UN mod F0. Okay. Now, what's with this map, this special point of URJ? So it was defined already in the mixed Tate case by Consistematio Unver. So when I was working with Don Cohen in the mixed Tate case, we were just using something that already existed. But now in general, we talked to them and they weren't, they gave us ideas, but they weren't really sure. And so basically what we did is we have defined it in general. And when I say soon forthcoming work, I mean, we have a draft, but let's say we want to just edit it a bit more before it goes in the archive. So, it would be great if we got it out next week, but, probably, as things are, it's probably going to take a little longer, but, early fall, let's say we should be out with this with the preprint that defines this period P and proves that it has the necessary properties. So now let me say a little bit about why. So this is a map from spec QP to URJ, map of schemes. Why do we call this a p-adic period map? Well, if we look instead of looking at the unipotent group, we look at its coordinate ring. So the coordinate ring of a group scheme is a Hopf algebra. I call it, that should not be AQJ, this should be ARJ. So below you see ARJ. I meant to write ARJ, at the top of this slide. Okay. It's a Hopf algebra, but because of the action of G on URJ, it has an action of G. So for P1 minus 3 points in the mixed Tate case, G is just GM, and an action of GM is just a grading. For a punctured elliptic curve, specifically non-CM punctured elliptic curve, it has a GL2 action, and more generally an action of your reductive group G. You can think of an action of a reductive group as like a generalization of a grading, because a grading is just an action of GM. And so the map period P, it should be a map of schemes going back from spec QP to URJ. Well, that's just the same as a ring homomorphism from ARJ to QP. Note, by the way, that ARJ is a Hopf algebra, but QP, we don't have any coproduct on QP. So we're not asking for this to be a Hopf algebra map in any sense. It doesn't respect any coproduct. We just want it to be a ring homomorphism. That's all. So why do I call it a p-adic period map? Well, it turns out that elements of ARJ can be seen as motivic periods, which was the idea of motivic periods goes back to Grothendieck and then Contsevich-Zagier in the a mixed case, and then Brown really defines something more similar to the kind that we're interested in. They're actually unipotent motivic periods in the sense of this is Francis Brown. They're unipotent motivic periods in the sense of one of Francis Brown's papers. And then this period P homomorphism sends a motivic period to the associated actual p-adic number. Okay, the actual p-adic period. Okay. And to relate back to the slide from way back when, remember I said that, I had this abstract form of the function with these CIs, but then I could say a little bit more about the CIs than just being p-adic numbers. Well, it turns out that these like F pi 0, F tau pi 0, all these weird F sub Greek letters with subscripts are specifically elements of ARJ. Okay, or p-adic periods of elements of ARJ. Okay, so that's where all that comes from. Now let me go and state the result of myself, the main result of my paper with Ishai Dan Cohen, or a special case. It's a little more general, but a key case of our result, which in fact it not just relates so it defines this period P and relates it not just to loc n, but in fact to kappa P in Kim's cutter, to the p-adic unipotent Albanese map, or unipotent Kumar map, as it's called. Okay, so here is the full statement of the theorem, okay, which is that there is a special p-adic point of URJ satisfying the following property. For any G equivariant cocycle, okay, like so, the composition where we first, so what do we do here? We have a map of schemes from spec QP to URJ. The cocycle itself is a map of schemes from URJ to UNDR. Then we apply projection from UN to UN mod F0. Okay. Altogether, what do we get? We get a map from spec QP to UN mod F0 UN. What is that? That is known as a QP point of UN mod F0 UN. Well, back in Kim's cutter, loc n goes from the Selmer variety to UN mod F0 of UN. One should maybe be more precise that it goes from, right, so it's a map of schemes, but if so when I'm talking about C, I really mean a QP point of, so it turns out that you can make the set of cocycles into a space of cocycles. And when I say C, I really mean, let's say, a QP point of the space, so a specific cocycle. And it gives you a QP point of UN mod F0 UN, which is exactly what you expect to get out of loc n. And so the theorem says that we can define this period P map from spec QP to URJ such that this composition is the same as loc n. Okay, and so again, the explicit result I had for an elliptic curve of a certain type depends on this theorem. So that's the extent to which my more explicit result depends on my work with Don Cohen and coming out in 2023. Okay, I hope it's coming out in 2023, and then we don't look back at this video and be like, oh, it didn't come out till 2025. But I have no reason to think it should be coming out within the next month or so. Great. Okay, so I guess I have a few more minutes. Okay, so this is the theorem, the sort of work of myself and Don Cohen that's coming out soon. So let me say that this results. The result of the previous slide, what it does in a sense is it reduces computation of the Chabauty-Kim ideal of the Chabauty-Kim functions of ICKR. It reduces it to computing a basis of ARJ, or really a basis of a part of ARJ depending on n, on which we know how to compute period P. Okay, now it turns out that the theorem that we prove is actually useful in doing so. Because how can I get an element of ARJ? Well, let's say I'm given a point on X. That should be really an X of R. So given Z an X of R, and some omega, which is going to be a function on U mod F0. So it can be, it's any such function is going to be on UN mod F0 UN for some n, but here I've just sort of taken the union of all of them. Okay, so what we can do is, well, kappa of Z is an element of this, is a point on the Selmer variety. In other words, it gives a cocycle. The cocycle is a map from URJ to u mod f0. So we can then pull back omega along kappa of z, along this cocycle, to get a function on urj, also known as an element of arj. And so we actually denote this by imb omega z. Okay, and this is following notation of maybe Goncharov and others. And it's known as a Motivic iterated integral. So you should think of it as being like the integral from b to z of omega. B, by the way, is the base point. When you do the Chabauty-Kim method, you have an underlying base point. So B is the underlying base point. And so then what happens is, specifically, is that this gives us an element of ARJ, and we know how to compute its p-adic period, because by the theorem, okay, its p-adic period is the Coleman integral from B to Z of omega. Okay? And there are methods of computing this due to many people, especially Jennifer Balakrishnan, and yeah. Now, I should just say that what's often going to happen is that X itself is not going to have enough R points, and it might even not have any. And so what you have to then do is consider maybe other varieties that have a similar kind of whose cohomology has similar Galois representations as the Galois representations appearing in X. And then I should say another sort of current challenge or challenge that we have to overcome before we do have a method for effective faultings is better understand the action of URJ on UN. Okay. Anyway, the eventual goal of all of this is an algorithm depending on the Bloch-Kato conjectures, which I said can be thought of as maybe a souped up version of the finiteness of Shaw. Okay, that under the same sort of halting conditions as before, or the sort of halting framework as before, give you the rational points on any hyperbolic curve X. Okay, so that's the long-term goal. And yeah, so here's a list of references. I have this preprint on archive. I have this thing on my website that will eventually go on archive. There's my thing with Ishai, which is not public, but will go on archive hopefully soon. And then there's the previous work of Don Cohen-Wevers and Don Cohen and myself, which is all, the other stuff was out for a long time and is in journals and on archive. And thank you. So I guess it's time for questions.
So thanks a lot for interesting talk. Are there any questions? Yeah, please.
I can't hear anything. I don't know if someone's speaking.
Yeah, wait, you'll be getting a question now. Yeah.
David?
Yes?
Thanks for the talk. I had a question. Yeah, for the, I think it was the next to last slide. Oh yeah, when you talked about replacing X by something else?
Yes.
Do you mean, for example, symmetric powers of the curve or?
For example, we're also like, you can think about the Jacobian, you can think about the complement of X in the Jacobian. You can also think about the the variety, the like Torsor over J that Edixhoven et al. And Edixhoven and Lido use. Right, and you can another thing that you might do. In fact, this is actually even more pertinent. Is you might consider X with a few more points removed.
Okay, maybe another question, a small one also. Could you explain a bit more?
Sorry, I accidentally muted. Sorry, I think the ICTS is muted. I'm so sorry. I was trying to move the screen. So whoever's asking the question is muted right now. Trying to move the screen and I accidentally pressed the mute button. Is the admin able to unmute them? Okay. Sorry, you can start your second question again.
Okay.
And by the way, who is asking the question?
Samuel Lefourne.
Okay.
Can you explain a bit more where the central formula of this slide comes from, given the properties here?
Which one? This?
The one where we retrieve the Coleman integral. Omega.
This just follows from the theorem in the previous slide and the commutativity of Kim's cutter.
Okay.
Yeah.
Right. Thank you.
Questions? Okay, let's thank the speaker. Thank you.